A colligative property is a collective property, which means you're actually measuring properties of a mixture, which is almost never done since the mixtures have properties which vary with the concentration. But if you know the concentration of both the solvent and the solute, you can see how that will affect boiling and freezing point. And what we will observe is that the boiling point will go up and the freezing point goes down, and that will therefore increase the liquid range. Let's solve a couple of problems and ask ourselves why. It could be that you're forming strong intermolecular forces that have to be overcome in order to boil that substance, so the boiling point of the mixture will go up. We can formulate this as the change in the boiling temperature, in which we might as well say increase since it will, is equal to some constant which shows how sensitive it is to this sort of effect. We'll call that K sub B, times the molality. It's handy to use a term where you can literally measure the solvent as well as the solute in a system. And that's the molality. So it's the moles of solute divided by kilograms of solvent. And PC is just a particle count. How many pieces does your substance break into when it dissolves in water? If it's an electrolyte, it would be at least 2. For example, sugar, well, it's not an electrolyte. It does not have ionic bonds, and therefore it's just 1. But you'll get 2 ions for each molecule of sodium chloride, and calcium chloride breaks down into 3 different ions. Let's solve a problem. What's the boiling point of a 2.75 molal aqueous sodium chloride solution? Well, the boiling point increase we'll figure out, then we'll tack it on to 100 to get the actual boiling point. This looks like direct plug-in since 0.512 can be found right there. That's the case of B for water. Molality is given at 2.75. And the ion count for sodium chloride is 2. It breaks up into sodium plus and Cl minus. That gives you 2.82 degrees, but you're not done. You have to add that to its normal boiling point to see how much it elevated it, and the answer is 102.82 degrees Celsius. Doing one more problem, very similar in nature. They will lower the freezing points, giving you a longer liquid range. Reason could be that it interferes with the crystal formation, and therefore it makes it harder for those crystals to form. You have to go down to a colder temperature before they do. The formula is exactly the same, only with F's rather than B's. And the terms are very much the same. The change in the freezing temperature is equal to some constant times the molality of the solution times the particle count. Once again, it can be 1, 2, or 3 for sugar, sodium chloride, and calcium chloride. Here's some constant data that you'll need to solve a problem, and here's a problem. What's the freezing point of that exact same 2.75 molal aqueous sodium chloride solution? Notice it's an intensive property, so the amount of that solution does not matter. The concentration of the solution does, and it's given. So let's plug in. Oh, looks like we're not going to get to see it. But briefly, if you look briefly, the answer is minus 10.22 degrees Celsius. Check that and see if you get the same answer.